the power rule, and more. The power rule can be considered the easy way of taking the derivative of power functions as opposed to the limit of a difference quotient definition that we used previously. So if I attempt to take the derivative with respect to x of a power function, which has to have a variable in the base and a real number in the exponent, well, we can simply take the derivative by bringing the exponent to the front through multiplication. So we can see that n is being multiplied by this x that's now raised to the new power of n minus 1. So we're simply subtracting 1 from the previous exponent. So it's really important that we know to use the power rule, the base must be a variable and the exponent must be a real number. And we'll go ahead and take a look at an example. If we're given f of x equals x to the fourth, so a variable in the base and a number in the exponent, find f prime of x, so find the derivative, and then find f prime of 2. So first things first, we're going to find f prime of x. So here we're going to go ahead and bring that power 4 to the front through multiplication. So we're going to have 4 times x. And then we would reduce the power by 1. We would subtract 1 from this exponent, so 4 minus 1. So in other words, my derivative is simply 4x to the third power. So that's my functional derivative as a function of x. Now I want specifically the numerical derivative, the slope of the tangent line at the x value 2. So f prime of 2 means substitute 2 into this functional derivative, so I have 4 times 2 cubed, or 32. So there are two different things that was being asked for, so there are two different answers, 4x cubed and 32. So it's really important that when I am asked to find the derivative at a numerical value, I first have to take the derivative and then I can plug in the particular x value. I can't plug in the number first and then take its derivative, or else I'm always going to get 0 out. As previously mentioned, we always want to find the derivative of a function before substituting in the numerical value if one is given. And then another big warning is that the power rule does not directly apply to an expression like quantity 2x plus 1 to the fifth. So for now, we would have to distribute this all out, multiply 2x plus 1 to itself 5 times and distribute until we get to a further rule in calculus for taking the derivative of something of this form. The derivative of the exponential function is the derivative with respect to x of e to the x is e to the x. So this is not a power rule. This is an exponential with a number e in the base and a variable x in the exponent, so it's its own special derivative. The derivative of e to the x is simply e to the x. And we're also going to add on some other properties of derivatives. If we have that f and g are differentiable, then if we have the sum or difference of f and g, that's also differentiable. And we can take the derivative of the sum or difference by taking the derivative of each one separately, is what this rule says. So if we have two functions added or subtracted, we can take the derivative of each one independently. And if we ever have a constant c being multiplied by some function f, we can simply take that constant out and then multiply it by whatever the derivative of the function is. So these are nice properties to have, and we're going to use them combined with the power rule in the next couple examples. In this example, we're given f of x equals 2x to the third plus 1 minus 3 over x to the third plus e to the x plus pi. And we're asked to find its derivative. So first we're going to rewrite the function. As you notice, it's already a sum or difference of a bunch of individual terms, and we can take the derivative of each piece separately. So I'm going to make sure each piece is set up so that I can apply the power rule. So 2x to the third is fine. It's a constant. And then I have a variable in the base, a number in the exponent. The constant by itself, 1, we can take the derivative of that. This piece here is what I have to rewrite. I'm going to rewrite it as negative 3x to the negative 3. So I couldn't leave it as it is as a quotient here and still apply the power rule. I need, again, a variable in the base and a number in the exponent, and it cannot be the situation where I take the derivative of the top and bottom of a fraction separately. And then e to the x is fine, and pi is fine as it is just a constant. So now we'll go ahead and take the derivative. Well, constants in the front of these variable terms, they just kind of hang out in front. So that 2 is just going to remain there. And the derivative of x to the third, well, we said we bring that 3 to the front and multiply it times x raised to the second power because that's 1 less than 3. And then now we'll take a look at the next term. We can do each one separate. Well, 1 is just a constant. So if I take the derivative of a constant, I end up with just 0. And moving on to the next term, this constant in front of the variable, negative 3, just hangs out in front as I apply the power rule to x to the negative 3. So it'll be times negative 3x. And then I'm going to subtract 1 from negative 3, leaving me with negative 4. And then we'll move on to taking the derivative of e to the x, which is just e to the x, so plus e to the x, plus, now pi is just a number, just like 1, so its derivative is also 0. So constants by themselves, their derivative is 0. When there's a constant in front of a variable function, that constant just comes right on down with it. And now we'll go ahead and simplify so we can multiply these coefficients. So we have 6x squared. Here the negative 3's multiply to become positive 9x to the fourth, to the negative 4, I'm sorry, plus e to the x. So we can go ahead and leave our answer like this. If we're going to do any simplifying, if we don't want any negative exponents, then we can rewrite it as 6x squared plus 9 over x to the positive 4, so only the x term moves to the bottom and the exponent becomes positive. The 9 stays on the top, and then plus e to the x. And the whole thing isn't over x to the fourth, just this middle term. So that's a somewhat common mistake. In this example, we're asked to find the derivative with respect to t of this collection of the sum and difference of these individual terms. So before I take the derivative, again, I'm going to rewrite each term so that it's set up for me to apply the power rule. So since I have not taken a derivative yet, I'm going to be really careful with the notation that I use. So I'm still leaving the operator ddt in front here. And then I'm going to rewrite each of these radicals so that they are fractional exponents. So I have t to the 1/2 plus here the cube root becomes 1/3, but there's already a 2 here, so my new exponent is t to the 2/3 plus, okay, I have just a t here. And then minus, well, there's no need to rewrite radical 2 because radical 2 is just a number. So when we take its derivative right now, it's going to become 0. And then this last piece here is going to be negative 2t to the negative 1/2. So when I bring that radical to the numerator, there was a 1/2 as its exponent. When it moves to the top, it becomes a negative exponent. So now I have variables in the base, numbers in the exponent, and I can go ahead and take the derivative. So now I'm not going to use I'm going to drop the operator because I'm actually taking the derivative of each piece. So here I'm going to multiply by the 1/2 in the front, so I have 1/2 t, and then I'm going to subtract 1. So I'm going to show this little bit of arithmetic here. So I have 1/2 minus 1, and then plus here I would bring the 2/3 to the front. So 2/3 times t, and then it'd be 2/3 minus 1, plus, in this piece I have just t. Well, technically I have t to the 1. So what's really going on here is I can think about the power rule as if I have 1t to the 1 minus 1, so that would of course be 0. Here, as I mentioned, this is just a constant, so its derivative is 0, so minus 0 plus 0. And then on this last term, I'm going to go ahead and leave the negative 2 in the front, and then I'm going to bring down the negative 1/2 through multiplication, and then t to the negative 1/2 minus 1. All right, so now we'll go ahead and actually perform the subtractions in the exponents. So I have 1/2 t, here we're going to have to the negative 1/2, plus 2/3 t, and then here we're going to have to the negative 1/3. And then right here, notice that I'm going to end up with t to the 0, and anything to the 0 is 1 times this 1, so we have just plus 1. We won't write the 0. And then here, negative 2 times negative 1/2 is just a positive 1, so we have plus t, and then negative 1/2 minus 1 is negative 3/2. So this is fine. You can go ahead and leave your answer with these negative and fractional exponents. If we wanted to do a little bit of simplifying here, we could rewrite this as 1 over 2 radical t plus 2 over 3, and then times the cube root of t plus 1, and then plus 1 over, we can go ahead and turn it back into a root, so we have the square root of t to the 3rd. So here would be more of a simplified version if we didn't want to leave any fractional exponents or negative exponents. In this example, we're asked to find y prime of negative 2, given y is equal to the quantity x minus 1 times the quantity 2x minus 3. So first things first is we have to take the derivative before we substitute in the numerical value. So to take the derivative of this function, first we have to turn it into a sum or difference of a bunch of terms. So right now we can't handle this product. We don't have a rule that says we can take the derivative of a product of each term separately. So what we have to do in order to apply the power rule is we have to distribute here. So we'd get 2x squared, and then outers minus 3x minus 2x, so minus 5x plus 3. So we would multiply it out first, distribute, and then we can find the derivative. We can find y prime. So notice this was still called y because it was just multiplying it out. Now I'm going to call it y prime. I'm going to take the derivative from one step to the next. So here, the derivative, so let's see if we can do this a little quicker. We're going to bring this 2 to the front, and it will multiply by this 2 that's already there. So let's just go ahead and simplify that to be 4x, and then it will end up being to the first power because we'll subtract 1 from 2. And on this term, negative 5x, well, again, it's negative 5x to the 1. So if we bring that 1 to the front and multiply it by this negative 5, we're just going to get negative 5. And if we reduce the power by 1, then I get x to the 0, and I wouldn't write x to the 0 because, of course, it's 1. And the derivative of a constant is just 0. So this is y prime, 4x minus 5, and I was interested in finding y prime of 2, or negative 2. So I can substitute negative 2 now into this x. So I get negative 8 minus 5, or the numerical derivative, negative 13. So the slope of the tangent line at negative 2 is negative 13. In this example, we want to find dy dx, or the derivative of y with respect to the variable x, given y equals ax squared plus bx plus c, all divided by the square root of x. So here, there's a couple different things going on. I have these extra variables here, a, b, and c, but we're not going to treat them as variables. We're going to treat them as constants, as if they were numerical values, because here we're told that we are treating x as the variable. In this notation, dy dx. So take the derivative of y and treat x as the variable. So we're going to leave a, b, and c, or think of them as constants. We also have a quotient, and we can't take the derivative of the numerator and denominator here separately. So what we have to do is a little algebraic simplification. So I'm going to rewrite this first. Since there's one term in the denominator, I can split this up to be ax squared over x to the 1/2, so I'm rewriting the radical as the fractional exponent 1/2, plus bx to the first power over x to the 1/2, plus c over x to the 1/2. So I haven't taken any derivatives yet. I'm just doing a little bit of simplification. And I'm not quite done yet. I mean, I still have quotients. Now I have 3 quotients. But what I can do is I can subtract, since these have the same base. If I move the x to the 1/2 to the numerator, it becomes x to the negative 1/2, and then I add those exponents. So what's really going to happen sort of all at one time, so this is going to become ax, and we have 2 minus 1/2, plus bx to the 1 minus 1/2. So I'm subtracting the bottom exponent from the top exponent. And then plus c, and then this last part just becomes cx to the negative 1/2. And then this is ax, so 2 minus 1/2 as a fraction is 3/2, plus bx to the positive 1/2, plus cx to the negative 1/2. So I've already done, 3 lines of work, which could be shortened. I was just showing the algebra here, but I haven't taken a derivative yet, is my point. So all I've done is simplified to get myself to a place where I can take the derivative. So now this was all equal to y equals, so now dy dx, the derivative of y with respect to x, is by the power rule. So we're going to bring the 3/2 to the front, and it gets multiplied by a. So it's going to be 3/2 a, and then x to the, if I subtract 1 from 3/2, I'll get positive 1/2. And then plus, we bring this 1/2 to the front and multiply times the b that's already there. And then x to the negative 1/2, because I'm subtracting 1 from 1/2. And then finally, this negative 1/2 gets multiplied by the c in front, and we'll have times x to the negative 3/2 if I subtract 1 from negative 1/2. So this is my derivative. And it required a little bit of algebra here in dealing with some fractional exponents. One of the common mistakes that I'll go ahead and put off to the side in red just to make clear that it's something that we cannot do is sometimes students tend to want to rewrite this as ax squared plus bx plus c, and then they do this, plus x to the negative 1/2, and they somehow bring this denominator to the top through addition. So this is not true. We cannot do this. We can't add x to the negative 1/2 on the outside. One way we can think about it is we are technically moving it to the top through multiplication, so x to the negative 1/2, but then even here we still have a product. So what happens too is students will bring it to the top through multiplication and then just take the derivative of each piece separately. So these is like 4 separate pieces, but this is a product, so we can't do that. So we'd have to distribute this x to the negative 1/2 to each piece to get a bunch of terms added or subtracted before we could apply the power rule to each individual piece. So a big problem with derivatives is really just that background knowledge, that algebraic simplification. So hopefully we cleared a little bit of that up. And this is my answer.
In this example, we want to find f prime of x, given f of x equals the quantity 2x minus 3 all squared, all over 4x. To apply the power rule, we're going to need to do some algebra. First, we'll multiply out the numerator. 2x minus 3 squared is 2x minus 3 times 2x minus 3, all over 4x. So we're going to have to distribute this out. So we're going to get 4x squared minus 6x plus 9, all over 4x. We have like terms in the middle, 4x squared minus 12x plus 9, all over 4x. Now, let's go ahead and split this up. So we have 4x squared divided by 4x minus 12x divided by 4x plus 9 divided by 4x. Simplifying further, well, 4 divided by 4 is 1. X squared divided by x, well, we're subtracting really the bottom exponent from the top one, so we're going to have just an x left over. And from the second term, 12 divided by 4 is 3, and the x's cancel, so we're going to have minus 3. And in the last term, 9 over 4 doesn't reduce, so we're just going to leave 9/4 as the coefficient, but we are going to go ahead and rewrite that x in the denominator. Since it's x to the first, when we bring it to the numerator, it's going to become x to the -1. Making sure that we are not also moving the 4 with the x. So 9/4 is a coefficient that stays in front, and just the x gets moved to the top and made into a negative exponent. So I haven't taken a single derivative yet. I've just done a lot of algebra to get myself to a point where I can take the derivative. So now f prime of x is equal to, well, the derivative of x, or x to the first, is just 1. So we can bring the 1 to the front, leave the x, and subtract 1 from the exponent, which would make it x to the 0. So that's why I have just a 1. The derivative of a constant is 0. And this part here will multiply that -1 to 9/4. So we have -1 times 9/4, -9/4, x to the -2. So I'm going to subtract 1 from -1. -1 minus 1 is -2. Now I can rewrite the second term so that it doesn't have a negative exponent. I can bring that back down and make it a positive exponent in the denominator. So that second term is 9 over 4x squared. And on this, I just want to show a little bit more algebra that I can do. I can combine these together to be one rational expression. So I can rewrite 1 as 4x squared over 4x squared so that these are fractions with common denominators. And now I have 4x squared minus 9 all over 4x squared. And I can even go a little bit further to be fully simplified. 4x squared minus 9 is the difference of squares. So it factors to 2x minus 3, 2x plus 3, all over 4x squared. So this is as simplified as an answer as we can get, but make sure that we're paying attention to the instructions. Often it will say that we can just leave the individual terms added or subtracted, but to avoid negative exponents. So it's often okay to potentially leave our answer like this, but just to review some algebra and more simplifying, we can also leave our answer like this. Higher derivatives. So far in our study of calculus, we have only found and analyzed first derivatives, but we can also find higher derivatives. We'll start by looking closely at the second derivative and talking about the notation. If f and f prime, which is the first derivative, are differentiable, then the second derivative is the derivative of the first derivative. So it should seem pretty intuitive. We just apply the differentiation process again to get to the next derivative. Here's the notation. So the prime notation looks like adding another one of those tick marks, looks like an apostrophe, right? And it's read as f double prime of x. So f double prime of x is equivalent to taking the derivative with respect to x of f prime of x. So taking the derivative of the first derivative. This is the prime notation on the function f. If we call the function y, then we can read this as y double prime. And we're going to go ahead and look closely at the Leibniz notation for second derivatives. So here we have the derivative with respect to x of dy dx. dy dx is f prime of x. So remember, f prime of x is the first derivative. dy dx is the first derivative. It's the derivative of y with respect to x. But there's an extra d dx in front because this is the operator that says do it again. Take the derivative of the first derivative. But to shorten this notation, what's happening is we have this notation here, which looks like d squared y all over dx squared. That's what it looks like, but it's really read as taking the second derivative of y with respect to x. So this is the second derivative, and in Leibniz notation, and then this is the second derivative using prime notation. Let's look at some examples. Find f double prime of x, so find the second derivative of f with respect to x, given f of x equals 2 times the square root of x times the quantity x minus 4. So here we're going to have to find the derivative 2 times. We want to apply the power rule in this case, but to do so we're going to need to distribute the 2 radical x to each term in the binomial x minus 4, because we need all of our terms added or subtracted only in order to use that power rule. Alright, so 2 radical x, that's 2x to the 1/2. So when I distribute 2x to the 1/2 times x to the first, we're going to add those exponents. So 1/2 plus 1 is 3/2. So this is 2x to the 3/2, and then minus 8x to the 1/2. So the 2 times 4 is where the 8's coming from, and then x to the 1/2. Notice that I did use an equal sign. I want to be careful about using equal signs correctly. I'm still equivalent to the original function here. I haven't taken a derivative yet. So I want to make sure that I don't put f prime of x, the first derivative, right away if I haven't taken a derivative yet. So now that I'm set up in a way where I have terms that are added together or subtracted, and I have a variable in the base and a number in the exponent on each of them, I can go ahead now and apply the power rule to find the first derivative. So now my label is going to say f prime of x. So I'm about to take the derivative, so this needs the f prime notation. I couldn't just write equal in this next step because I'm about to take a derivative. We're going to bring this 3 over 2 to the front and multiply it to the 2. So 3 over 2 times 2x to the 1/2. So I multiply the 3 over 2 to the front and subtract 1 from the exponent. Subtracting 1 is subtracting 2 over 2 from 3 over 2. So I have 1 over 2 left. And then on the second term, same thing, multiply the 1/2 to the front. So minus 1/2 times 8x to the negative 1/2. If I subtract 1 from 1/2, I get negative 1/2. We want to be pretty good at subtracting these simple fractions, subtracting 1 from simple fractions like this, to be able to do it in our head. Similarly, we want to be able to do this multiplication in our head as well, like 3/2 times 2 is simply 3. So 3x to the 1/2 minus 4x to the negative 1/2. Again, this is still equal to the previous line. This is just a simplified version of the first derivative. It is set up perfectly for me to take the second derivative now. I have 2 terms added or subtracted with a variable in the base and a number in the exponent. So I will move on now to finding f double prime of x. F double prime of x is going to be multiplying the 1/2 to the 3 in the front. And so let's try to do that mental math now. So here I showed the work. Let's try to do it in our head. So 3 times 1/2, that's 3/2 x. And then I'm going to subtract 1 from 1/2. So that's going to give me a negative 1/2. And then on the second term, I'm going to multiply negative 1/2 times negative 4. That's a positive 2. And we're going to have x to the negative 3 over 2. Subtracting 1 is subtracting 2 over 2. So negative 1 over 2 minus 2 over 2 is negative 3 over 2. Often you'll see the answer left like this, even though it's not simplified, even though I have some negative exponents left. If we wanted to do just a little bit of simplification, or just for practice on seeing an alternate version of the answer, we could see it written as 3 over 2 radical x. So bringing x to the negative 1/2 to the bottom, making it positive and turning it back into a square root. And then plus 2 over the square root of x cubed. So bringing x to the 3/2 to the bottom, but then turning the 3 over 2 exponent into the square root of x cubed. So these are equivalent versions, just one is a little bit more simplified of a second derivative. So just some things to be cautious of, right? Correctly using your equal signs, and then correctly labeling when you've taken the first derivative, when you've taken the second derivative. Let's look at another example of finding the second derivative. Here we have the Leibniz notation. So this is a notation that's telling us take the second derivative and treat x as the variable. And here's the function. So in order to use the power rule here, I'm going to have to rewrite this first term. So I have terms added or subtracted, that's great, but the first term isn't written in a way to apply the power rule directly. So what I'm going to have to do is rewrite the first term. Well, I haven't taken the derivative yet, so I still have to put this notation in front because I haven't done that operation yet. This is an operator. So I'm going to rewrite this as 3 over 2 x to the negative 2 minus 2e to the x. So all I've really done is rewrite this. I've brought the x squared to the top and made the exponent negative. Now the 2 does not move to the top. I'm not entirely sure why, but people want to move the 2 to the top. I'm only able to move x to the second power to the top, and therefore making it a negative exponent. So now I can apply the power rule, and if I do that, that means I will have taken one derivative. So my notation will become just d dx. So it's like I've peeled off one layer, and then the derivative will be, let's go ahead and practice again, doing it in our head. If I bring the negative 2 to the front and multiply, the 2's will cancel, so I'll get negative 3x to the negative 3. I'm subtracting 1 from negative 2. That makes it more negative. And the second term is not a power rule because it's a general exponential function. So the derivative of the exponential function, just e to the x, is e to the x. And remember, constants just stay in front of the function. So this is the exact same thing. Negative 2 or minus 2 e to the x. So we've done the first derivative here. Now there's one operator left, so take the derivative one more time. And by the power rule on this first term, negative 3 times negative 3 is positive 9. X to the negative 4, if I subtract 1 from negative 3. And again, the derivative of 2e to the x is 2e to the x. So same thing, minus 2e to the x. So the operator is gone completely because I've performed the operation. I took the second derivative. So here is my answer. And again, I can go ahead. All right, let's generalize things now. We can find even higher derivatives. So the higher derivatives, f double prime, f triple prime, the fourth derivative of f, they're all defined by successive differentiation. So here we looked at, this is the second derivative of y with respect to x, or f double prime of x, the derivative of the first derivative. If we change all those to 3's, now I have the third derivative of y with respect to x, f triple prime, that's the derivative of the second derivative. Right? The derivative of the second derivative gives you the third derivative. And we can keep going. We can find the nth derivative. So the nth derivative would be denoted f, and then n represents whatever derivative we're taking of x. and then using Leibniz notation, we'd see the d with the n in the power position of the function y with respect to x as the variable. So we can just do the successive differentiation. With prime notation, we stop at 3 little tick marks, and then once we get to a derivative higher than that, we would just put the number in parentheses here, because we're not going to, put the 7th derivative and put like 7 little tick marks just because it's going to take forever. So that's the prime notation past 3. Let's do some examples of higher derivatives now. So here, this is the 4th derivative of f with respect to x. Given f of x is x cubed minus 3x plus 5. This is set up perfectly to apply the power rule right away. I have terms added or subtracted, and then with a variable in the base and a number in the exponent. So we will start with the first derivative. F prime of x is, bring that 3 to the front, subtract 1 from the power, so 3x squared. And then the derivative of negative 3x, well, that's just going to be negative 3. If we apply the power rule, we think about bringing that 1 to the front, which keeps it 3. And then x to the 0, if I subtract 1, then anything to the 0 is 1. So just minus 3 here. And the derivative of a constant is 0. So here, I'm not going to have any piece to my first derivative. So here's my first derivative, and then I keep going. So we have f double prime of x. By the power rule, 2 times 3 is 6. So we have 6x to the first. We never really write the first power, so we'll just put 6x. Now this constant 3, its derivative is 0, so we're not going to write anything there. And then the third derivative, so f triple prime of x, well, that's just going to be 6. So here, there's a 1 up in the exponent. 1 times 6, that's 6. And then we have x to the 0. Anything to the 0 is 1. Also just the derivative of a linear function. 6x is linear. It's just the slope, right? So we just get 6. And then the fourth derivative, which we're going to write with that little 4 up in the exponent, is just 0. Because now 6 is a constant. So the derivative of a constant, like the slope of a constant, is 0. So my fourth derivative ended up being 0. And in our other example here of a higher derivative, I am being told to find the third derivative of the function y with respect to x, but this time at the x value 1. So after finding the third derivative, then we would plug in the x value 1. We do not plug in 1 right away, which is a common mistake kind of early on in calculus, because if you plug in 1 right away, now you just get a number, like y is equal to a number, and the derivative of a number is 0. So we can't plug in the 1 first. It's first take the third derivative with respect to x of y, then plug in 1. Now here, 3 plus 4 over x all squared, that's not set up for us in a way to apply the power rule. So we are going to go ahead and multiply this out so we get a bunch of terms added or subtracted. So we're not taking a derivative yet. I'm just going to put equals. So I have 1 plus 4 over, 3 plus 4 over x, times 3 plus 4 over x. So quick reminder, I can't distribute an exponent, so I can't square each of these. This is requiring me to distribute out. So when I do that, I'm going to get 9, so 3 times 3, and then plus outer, that's going to give me 12 over x, plus inner is also 12 over x, plus last is 16 over x squared. So where am I at? I have 9 plus, these have common denominators, so they are like terms. I have 24 over x plus 16 over x squared. I haven't taken a derivative yet. I'm just rewriting it so that I can apply the power rule. I have one more thing to do before I can apply the power rule, which is rewrite 24 over x as 24x to the negative 1, so that I have that variable in the base and a number in the exponent. And same thing with the last term. So plus 16x to the negative 2. Whew, okay, so really, that was all just algebra. You didn't have to necessarily show all this work. A lot could have been done in your head, but I just wanted to write it all out for review. To make space, I'm going to clear this out and just leave that final 3 terms that we're going to differentiate. So let's go ahead and start differentiating. So the first derivative would be y prime. Since we're using this Leibniz notation, I'm going to put dy dx is equal to, so remember, y prime is the same as f prime, is the same as dy dx, but I'm going to stick to dy dx notation. The derivative of a constant is 0. The power rule here says bring the negative 1 to the front. So negative 24 x to the negative 2. And then negative 2 times 16, that's negative 32 x to the negative 3. There's my first derivative. Take the second derivative. I have the second derivative of y with respect to x. By the power rule again, let's bring that negative 2, multiply it times negative 24, that's a positive 48, x to the negative 3. Subtracting 1 from negative 2, I get negative 3. Then we're going to multiply negative 3 times negative 32, that's positive 96 x to the negative 4. And then we do it one more time for the third derivative. So here we're going to have the third derivative of y with respect to x is equal to 48 times negative 3, that's negative 144 x to the negative 4. If I subtract 1 there. And then I have 4 times 96 is 384, but it's going to be negative 384 x to the negative 5. Ooh, okay. So the last thing is to plug in x equals 1 into each x. So here I have, negative 144 over 1 to the 4th. So let's see. d3y over dx cubed when x is equal to 1. So I'm plugging in 1 here. I'm thinking about, that would be 1 to the positive 4 if it's on the bottom. And then minus 384 over 1 to the positive 5th. So really it's just negative 144 minus 384. Negative 528. So my answer was a specific number because I was plugging in a number into the derivative, the third derivative.